Okay, so it's a pleasure to be here. So I want to talk, this talk is mostly motivated by quantum field theory, in particular non-perturbative dynamics of quantum field theories is what I'm mostly interested in. This is a fundamental and still largely open problem. And I don't have to motivate, I think, a lot the importance of these problems in this audience. The ability to solve specific QFTs, gauge theories, for example, and discover new ones like non-Lagrangian ones that are more exotic is important for theory and applications. One class of lessons that we have been learning over the years is due to all sorts of different, very interesting dualities between different types of quantum systems. Dualities between quantum field theories and quantum field theories, or dualities between quantum field theories and gravitational theories like the ADA-CFT. This is very important because it teaches us a lot of new conceptual lessons. We get a lot of new conceptual lessons about what it means to do non-perturbative quantum field theory, but it's also useful practically because it gives a second life to perturbation theory. Now we can use perturbation theory in the dual description to extract non-perturbative information. But it's also true that in all sorts of, the large majority of dualities that we formulate, we rarely can go beyond the status of well-motivated conjecture, so we cannot prove them. So despite the significant and impressive progress, the available truly non-perturbative tools that we have available is limited. Here are some examples. Numerical methods like lattice field theory. This is usually what we have in mind when we say, oh, we'll take this theory and we'll put it in a computer. Have well-known limitations and are intimately tied to traditional approaches. For example, we cannot use them to study exotic quantum field theories like the 6D 2,0 theory because there's no path integral, which we will compute with the lattice field theory method. Special tools like those based on supersymmetry, integrability, anomalies, have provided a lot of very interesting, beautiful, useful information, but do not allow us to have full access to generic theories and observables. Bootstrap methods that I will come back to are very, very promising. They are truly non-perturbative, but they are not yet at the level where they can solve an arbitrary theory. So this is basically the invitation part of my talk. So it's clear that we have been making a lot of progress, understanding all sorts of different non-trivial aspects of quantum field theory, but it's also clear that it is difficult to go beyond the state of the art. It is clear that we need new ideas. And that's the main question here is, can we think of new ways to solve quantum field theories? One, let's say, naive idea is maybe we can view QFTs as big data structures that can be learned. And this is exciting because basically of the particular circumstance of what's happening in computer science. In computer science, there is a lot of progress, all sorts of interesting, amazing things are happening. So it's natural to ask whether we can use them, things like, for example, from machine learning or AI, to solve quantum field theories. And this also connects to Magdalena's talk. But here the focus is not so much on string theory, but quantum field theory itself. So, okay, so that's a natural question, but exactly what should we aim to learn and how? So here are 3 points. So one thing we can try to do is we can try to solve all problems in new ways. So for example, we can go back to lattice field theory and we can try to improve sampling processes, like use ML methods to do that, and this is something that people have been thinking about. Another thing that we can think about is we can do with ML methods is to perform more efficient searches of solutions. When you have a large landscape of configurations and you search for specific ones and the search problem is very hard, ML methods have proved to be a very useful alternative. And for many examples in string theory, you can take a look at Magdalena's talk or Fabian Rule's review from 2020. Now, since the focus here is on quantum field theories, I want to highlight a particular direction, which we have started studying with Kostis Papageorgiakis at Queen Mary, but it's basically quite an open direction yet. Like, how do we apply such methods in conformal field theory? In conformal field theory, in particular in the conformal bootstrap program, basically what we're doing is that we're trying to find consistent CFT data. What are the CFT data? Scaling dimensions and 3-point function coefficients. And we try to constrain them using principles of symmetry, like crossing symmetry, for example, or any other relation, generic relation that we have. And so you can think about it as some very complicated sets in the configuration space of all possible CFT data, and there you need to select the ones that are consistent. And this is precisely the logic that we try to follow with Kostis in a series of papers. And in particular, one of the things that we're doing there, we are exploring adiabatic deformations from tractable to intractable regimes, from weak coupling to strong coupling, tracking the evolution of solutions of interest across parameter space. And we use reinforcement learning algorithms to do that. The way we do it is completely different from the standard approach. Instead of making some assumptions that then we eliminate, doing the standard semi-definite programming methods, what we are trying to do is we are actually trying to truncate the spectrum, write down explicitly the crossing equations, do a careful, so we do not do hard truncations. We try to also estimate tails, et cetera, but we are actually trying to solve explicitly the crossing equations. And then we're doing a search on CFT data that will satisfy the equations. So doing things like this has the obvious advantage, it's non-rigorous, but has the obvious advantage that you don't need positivity. So you can apply this in many situations where the current bootstrap doesn't go, for example, in the case of boundaries or finite temperature or whatever. And one of the places where we got very promising results is this one, the last paper, where we applied it to the bootstrapability context. So we analyzed correlation functions on half BPS Wilson lines in n equals 4 per Yang-Mills theory. This method can reproduce, without using positivity, the same results that Nikolai Gromov got at King's, at the same accuracy, like at the accuracy for some data of the 7th digit, but with much, much less computational cost. For example, the standard semi-definite programming methods require digit precision at every step of hundreds of digits. They were using 1,000 digits. We did it with just machine precision, 16 digits, and we got the same results. In some cases, were even better. So the key question for the future in this context is, basically, in the previous slide, I was sort of critical about all these methods that we're using so far, that they do not allow us access, and now I basically want to turn it around. Basically, now it seems the key point for the future is, can we take all of these results that we are obtaining with special tools, in special corners, and then bring them together under some other strategy, more general strategy, that will use this specific information to make the searches more informed, improve the searches, and give us access to all the other data that we cannot access at the moment. And this is, in fact, I think, the current trend in general in the conformal bootstrap program, how you inform the searches with the information you already have. Now, a third thing that you can do is you can try to learn new structures in some tractable corner. So you have a complicated problem, you can only solve it in some corner. And then there you can try to learn a new structure and then attempt to generalize it, generating new solutions in previously inaccessible regimes. Generalization is a central problem in artificial intelligence. And it could be very interesting in this context where also generative AI techniques might be useful. So in the rest of this talk, I want to stay with this third point, and I want to give you a very specific example of how, or one particular example of how one could explore this in a very specific, simple problem. So let me first explain this toy problem. So this is based on recent work with Kostis Papageorgakis that was recently posted on the archive. So let's go to, I will phrase it in the language of quantum mechanics. So we will consider elastic 2-to-2 scattering in quantum mechanics. And one of the things that we compute there is the differential cross-section. It is directly expressed in terms of the square of the scattering amplitude. The scattering amplitude depends on the scattering angle, theta. I will use z, which is cosine of theta. So experimentally, we measure the differential cross-section, and we learn about the modulus of the scattering amplitude, which is a complex quantity. Since it's a complex quantity, it has a modulus, it has a phase, and the very basic question you can ask is, if you have the experimental data of the modulus, can you reconstruct, say at fixed energy, also the phase of the scattering amplitude and therefore the whole scattering amplitude? So the two quantities, the modulus and the phase, are intimately related to each other. How do you know? For example, if you use a partial wave expansion, then you express everything in terms of phase shifts. And if you have the phase shifts, then you can take the imaginary part. You can take, you can compute the modulus, you can compute the phase, and everything is expressed in terms of the phase shifts. Now, this is easy to do if you have a finite partial wave expansion. So if you want, for our case here, this will be the tractable regime. You have a finite partial wave expansion, and you can analyze everything. The problem is much harder for generic amplitudes that have an infinite partial wave expansion, which is the generic case. This problem is not new. It was studied in the 60s and 70s when people were trying to analyze, as Ruth mentioned in the morning, the analytic properties of the Earth matrix by people like Martin, Atkinson, and others. And the standard approach goes like this. Again, as we heard in the morning, unitarity plays a very crucial role. So if you rewrite unitarity in this context, it gives you a direct relation between the phase and the modulus, and the relation is an integral relation of this form. It's not the worst relation you have seen, but it's not also straightforward. You can see that it's non-linear, it involves a double integral. Also notice that we integrate over zeta1 and phi1. Zeta2 is expressed in terms of z, zeta1 and phi1 in this way. So what people were doing in the 60s and 70s was to analyze this equation. So the analysis of this equation quickly yields some interesting results. For example, if I set z equals 1, then this factor goes. Z2 equals Z1, so therefore the cosine also goes because it's 1. And there, sine of phi is an integral, a double integral, or an integral of the modulus B. And since it's supposed to be a sine, it must be less or equal than 1. So if you give me some B that doesn't satisfy its inequality, I cannot solve the problem. Now, you can get additional bounds. For example, on existence and uniqueness of the phase. For example, if I define this function, which is a previous integral without the cosine, then I can take the maximum value of this function. It's called the Martin parameter. And for formal reasons, I denote it as a sine of a parameter mu. When the sine of mu is less or equal than 1, then you can show that you can find a unique solution. When sine of mu is greater than 1, solutions may or may not exist. When they exist, they can be unique or doubly ambiguous. And in general, it is unclear what happens. Okay, it's not an easy problem. Okay, so can we solve it? So that's the problem. First of all, what is the traditional way of solving, the traditional thinking about solving this problem? Well, we can use ML, for example. And again, as you heard from Magdalena's talk, neural networks are good approximators of functions. So the unknown function, we're given B, so we need to find phi. Phi is the unknown function. We can use a neural network to model the unknown function. So we model phi by a neural network that has some parameters theta. We formulate a loss function, which is basically how well we satisfy this equation. And then we try to optimize the parameters of the neural network in order to satisfy, in order to bring this loss as much as, to make it as low as possible. So we turn this problem into an optimization problem. Finding the optimum neural network parameters is called training and involves solving a generally hard non-convex optimization problem. This is precisely the type of problem that recent ML progress has been able to solve. So this approach is called a PIN, a physics-informed neural network, and is a standard neural network method for solving PDEs. Here we're not solving a PDE, we're solving an integral equation, but it doesn't matter. This approach was recently used by Sasha Ziboevdov and collaborators to revisit this unitarity equation and solve it using a neural network. And they produced some very nice results. For example, One important question here is, I told you that for sign mu greater than 1, you have ambiguous solutions. Give me a B, I can find two Bs. And these are very special configurations. So you can ask, what is the smallest possible value of the Martin parameter where you can achieve these doubly ambiguous solutions? And the previous bound was, I think, sign mu, which was around 2.15. So these guys were able to find a new solution, new configuration, with an even lower bound, improving the bound after 50 years. Okay, also note that this approach requires retraining from scratch for each new input B that you give me. So every time you give me a new B, I have to solve the problem from the beginning, right? So, which is a time-consuming process. Okay, now, what I said is basically the description of the problem, but it's not exactly what I want to do. Remember, my point 3 was you have some tractable corner, you want to discover some new structure, and then you want to solve it. So here, the tractable corner is the finite partial wave expansion situation. The structure that plays a key role here is the unitarity equation. So I want to do something slightly more ambitious. So now we'll play a game where we assume that the unitarity equation is not known. Okay? In this problem, it's known, so we're using it as a toy problem, but in many other problems that we care about, we don't know that equation, and we want to discover it. So the only tractable information that we will allow ourselves to have access to comes from finite partial wave expansions. And the question is, if I give you only finite partial wave expansions, can you discover this equation and solve it? You're not allowed to use that equation, okay? Now, why is this interesting? Because more generally, because what I'm really trying to learn here is not model a function, phi of z, for example, but really learn a map, an operator, between two types of functions. So I'm really trying to learn maps between infinite dimensional spaces of functions, which is also interesting from a continuum QFT perspective, again, as we heard in the morning, because QFTs are naturally structures operating on such spaces. Like you take a path integral, you operate on functions. So understanding how to do efficient manipulations with functions or learning functions is important in general. Okay, so can we do this? And the answer is yes. So in computer science, there is a more general neural network architecture, which is called the neural operator, which does exactly that. In usual neural networks, you start from an x, and you go to the function f of x. This is what you model. But here, you have another architecture. I display it here with a black box, that starts from an input function, or a set of input functions, and go to a set of output functions. The architecture of this is more complicated. It's a more complicated architecture. It has linear operations. It has non-linear activations, but it also has integral transforms. So it acts non-locally on the space of x's. In this case, we are not supposed to have the equation, so I cannot put it in a loss. I can only do supervised learning, so I can show it a lot of examples. What kind of examples? The ones I have access to with finite partial wave expansions, where I show it a lot of B's and phi's, okay? And I train only once. Once I trained, I can use it to make predictions in less than a second, okay? Another cool feature that this has is zero-shot super resolution. In order to put it in a computer, I have to discretize the space of x's, or the z, here, okay? But this thing has been typically used to solve PDEs, like the Navier-Stokes equations. You can solve the problem, or you can show it samples in some low resolution, and then it will produce very efficiently predictions for higher resolutions. So this is called zero-shot super resolution. Okay, so let me show you some examples, and then I will conclude. So let's do that. So one of the things we did is we took one of these neural operators called Fourier neural operator. It does basically all these integral transforms in Fourier space. That's why it's called the Fourier neural operator. We trained it on 300,000 B-phi's, which consisted of 100,000 L equals 1 amplitudes, and 100,000 L equals 2 amplitudes, and 100,000 L equals 3 amplitudes. We had to use GPUs on a cluster to do that. And we discretized for this exercise Z on a uniform grid with 100 points. Okay, so we do the training. we reserve some data, some samples to do testing. And this is an example of three of tests where you can see in orange and blue the prediction and the ground truth, and basically they're on top of each other. The accuracy is at the level of 1%. And so that's a signal that it has trained well, okay, on finite partial wave. Now, how does it generalize? That was the main question. That's what I'm trying to probe. How does it generalize? Does it allow me to learn about scattering amplitudes that have an infinite partial wave expansion, which is supposed to be the hard thing? And here are two examples, one with a linear B, z plus 4 over 10, and one quadratic B, z squared plus 1 over 2. We selected this because it's also what Ziboedov and company have as examples. And you can see again that they are on top of each other, so it has predicted well. Okay? Again, at the level of 1% or 1,000. We can do more. We can do a scan, very quick scans, over lots of linear and quadratic moduli. This is the linear, this is the quadratic. And here, for the moment, I'm allowing myself to use the unitarity equation to see how well I'm performing. So you can see that I get lower losses precisely inside this I, which is precisely the region where sine mu is less than 1, which is precisely where I expect to find solutions. So these two plots, and everything is bad outside the dual bound. This is the dual bound, and these curves are sine mu equals 1. So it seems to be performing quite well, and qualitatively it has the right features, and I will show you later the corresponding plots with the pins of Ziboedov and company. Now, this is promising, but I cheated, okay? The first problem is that I told you I cannot use the unitarity equation. So if I cannot use the unitarity equation, how can I check that I made a good prediction? Also, in some cases, there should be no prediction because there's no solution. But the neural operator will be producing predictions. Another question is, okay, here in these examples, it seems that the neural operator performed well, but does it perform well everywhere? And you can check that the answer is no. For example, if you test on higher L finite partial wave expansions, it performs poorly. So it has learned something non-trivial, but not the complete information that the unitarity equation has. Okay? So I need more. What do I need? I need the ability to, I want the neural operator to rate itself, to be conscious of whether a prediction is good or bad. So here, we went a step further in a rather non-standard application of neural operators to do the following. So we do not only train the neural operator showing it what it means to succeed, but we also show it what it means to fail. Okay? And that gives it the ability to learn both good and bad predictions. So let's redo the exercise. Now we train on 400,000 samples with the following composition, 225,000 true samples like the ones before, and 175,000 false samples. And when it makes a prediction, it produces a prediction for the face, but also a label, like dog, cat, that tells you, is it a good prediction or a bad prediction? And when we train on the true samples with f equals 1, we call it a fidelity index. When we show it false examples, we set the label to 0. We find that we get much better reliability from F when we average over several neural operators. So the collective information from neural operators is a useful thing. This is also something that we learned in the bootstrap exercise with the reinforcement learning. We're getting better results when we had lots of agents exploring the landscape of safety data. Within the training data set, we also noticed the following thing. What we mostly care about is how reliably does the neural operator predict that the solution exists. So this will happen when f bar, this fidelity index, is very close to 1. So let's say f bar between 0.99 and 1.01. Okay? It's very close to 1, so it's supposed to be predicting that it's a good solution. So in the test sample, how many times was this correct? How many times was it predicting a correct solution? It was actually a correct solution. The answer was 98.6% of the time. Okay, so we also find if you also bring in the unitarity loss and compare, you also see that there is a strong correlation between the fidelity index and the unitarity loss. So now let me go back to these plots in the linear and quadratic moduli case. And now, again, I don't have access to the unitarity loss, so I'll plot the fidelity index. And the fidelity index does exactly, well, at least approximately, does what I wanted to do. It isolates an island of good predictions. And this island is very close to the expected one. Here is the plot I had before. This is the plot I had before here. But now I show you the even better plot of Ziboedov and company. It's basically the same plot. The loss is much better because they're solving a dedicated problem for every B, where we trained only once. That's the main difference, but otherwise it's very similar. Also notice that this is more granular because every time they have to resolve the problem again and again, whereas we can evaluate immediately. Okay, good. Now, if I show you the quadratic case, it's even more interesting. This is a harder case. I'm finishing in 3 minutes. So this is an even harder case, even for the pin case. When psi mu becomes larger, they have harder time to find solutions. Notice what was my plot was this one. It had this region and basically nothing else, no other feature. These guys find more features. They find this feature, they find 2 islands here, and then this curve here. Then they realize that these points here are spurious. They're basically some configurations, some scattering amplitudes that are numerically, they happen numerically to be close. They're finite partial wave expansions, but they happen to be close to these quadratic ones. So they shouldn't be there, but for some numerical accident, they are there, they are detected. But these 2 islands are actual solutions. They're in fact finite L equals 2 scattering amplitudes that have a quadratic B. What did the neural operator with a fidelity index do? It has a very similar thing like this one, but now it actually managed to detect also this other 2 L equals 2 features. So the presence of the fidelity index not only gives you reliability on when you should accept or reject a solution, but seems to also have affected the qualitative features of the prediction. Okay, and then you can do also some things with ambiguous phases. I will skip that. You can see the lectures if you want, or the paper. So this was just an example, just to give you a flavor of the different things we can do. So what was interesting to me here is not to solve this particular equation. I did not contribute too much to the existing knowledge. What is interesting is that I try to solve the equation without using the equation. And in many cases, we do not understand the structure well enough to solve the corresponding equation. Okay? So there are many more things to explore. For example, a couple of days ago, there was a paper by Lance Dixon who is using transformers for the first time to study the amplitudes bootstrap. And notice the paper is not in the HEP-TH, it's in the computer science section. There is a reason I think other fields have adopted these methods much more quickly than us, and I think there's an obvious reason for that. Our field is not naturally data-driven. It requires rigor and integrability. These are things that we like. ML methods, as you also saw in some of the examples I gave, are usually stochastic and error-prone. But I should emphasize that there are examples of rigor and interpretability in ML and AI. And I invite you to see a recent perspective article on this, emphasizing this point by Gukov, Halverson, and Rille. What is most exciting to me here is not that I will have some new numerical method to get numerical results. I'm more of an analytic person. What is exciting to me is that I'm trying to apply unorthodox approaches to a challenging mathematical and physical problem, and this, unlike other fields, doesn't happen automatically. It will require us to rethink the kinds of problems we're trying to solve and reformulate them, and that, I think, might lead to considerable conceptual gains. Non-perturbative QFTs pose a plethora of such challenging problems, and it's mostly an unexplored area with these methods. This is my last slide. And personally, I find the conformal bootstrap a particularly interesting context to apply such methods because it is genuinely a non-perturbative approach. And I will end with 3 questions. Can we bring together the progress of recent years in SUSY QFT, ADCFT, analytical numerical bootstrap, integrability to devise new strategies and to extend, generalize the knowledge of tractable corners into generic inaccessible regimes? That will give even higher value to the stuff that we are already doing. Another more specific question, can we use ML and AI to improve the numerical bootstrap on the technical front? It's already reaching a stage where it's becoming harder and harder to do higher multi-correlator bootstrap calculations. How will the interplay between numerics and analytics evolve? Another question, can we apply similar methods to more general QFTs? The S-matrix bootstrap is an obvious target. And I'll stop here. Thank you.
Thank you very much. Questions?
Thanks for a nice talk. I don't know if this is a meaningful question, but I still ask it. So, in your example, what's sort of the dependence on the L values that you train your data on? You chose L equals 1, 2, 3.
Yeah,
said,
the reason
right?
why we chose, in the beginning we tried more L's, but if you plot higher L's, you will see that they are they are functions that have lots of kings and they are almost discontinuous, and it made learning much, much harder. So we went up to L equals 3 where it was sensible. I mean, it still has kings and stuff, but not too complicated. And that's why we trained up to L equals 3. But one could try to, one thing that I try to emphasize here is that you get this neural operator, you get this fidelity index or whatever, which is quantity. I like to view it as some new neural network motivated assigned new parameter. Okay, but it doesn't depend only on the physics, it also depends on the learners you used. So it's like you're trying to solve a problem and then you have 2 groups or 3 groups, and some people, group 1 learns this kind of thing, group 2 learns this thing, etc. So you get these quantities that depend on the learners. So you could try to do a different type of training with different hyperparameters, different samplings, etc. You would, I think, get a different you will extract different information from the problem.
Okay, thanks.
There's another hard problem in quantum mechanics, reconstructing the potential from unknown amplitude. Has anyone tried to do it using machine learning?
I don't know. One can try. Yeah, that's indeed an interesting inverse scattering problem. Yeah. Yeah, one could try. All sorts of different things you can try.
More questions?
The question is, what does it mean for a physicist to solve a system? So suppose you have all this nice method, you get some results, but unless you have some ways to interpret this result or to have some simple model that explain it,
that's right. Yeah, that was this point here. It's not always interpretability is not always obvious here, so it requires further work.
Which you cannot do using this AI and.
Well, we don't know yet, right? Because if you ask ChatGPT, you get some answers that surprise you. So, so it's clear that this thing at this moment, in some sense, it's not very impressive, right? Because the whole AI business, ML business, is mostly about fitting things, right? But now it's reaching a level where this fitting becomes impressive and it's highly non-trivial. So what will happen in the future is not clear. Interpretability, there are mathematical problems like Magdalena was talking about, an example where you actually get you identify some structure. It's not clear what, if this is an actual conjecture. It makes a conjecture in mathematics and then you bring in the human in the loop and then you get interpretability. All these are part of the game here. But I think what is most interesting to me is the fact that in order to use these methods, we cannot just use them like astrophysicists. They just do signal analysis, right? They just take this method, they do a standard thing. In our case, we have to rethink how to posit the problem, and also, what kind of analytics or extra numerics are we going to use to make the search better or the problem better defined? And that, I think, is a very useful exercise.
Any more questions? All right, if not, let's thank Vasilis again.